Okay, exponential growth and decay. Exponential growth and decay is huge. Very, very important stuff. Very simple. Much, much easier to deal with than a lot of the more complicated polynomial stuff and radical stuff that we've dealt with earlier. Okay. I don't know. You might have to go to a different room. This hill, it's important because it describes the way the world really works. A lot of the behavior of economic markets, biological growth of populations, radioactive decay, all that stuff obeys this kind of a model. So let's take a look at this. Here's the equation, very simple equation that models exponential growth and decay. Y equals a times b to the x. Now what's odd about this is that the x is in the exponent. The variable is in the exponent. You're not used to that. In the past, we've always dealt with functions where we've had maybe a variable or a constant to a constant power, right? Like in a polynomial, for example. All the exponents were natural numbers, right, or whole numbers. In this case, the variable is the exponent, so that's the key difference. Okay, what do these things mean? Well, the number out front, the multiplier out front, that's called the start value or the initial value. So when we look at these examples, that's going to be when we start keeping track, when time is equal to 0, the first year 0 or second 0 or whatever we're measuring time in. When we start measuring, that's the value of the quantity that we're looking at. B, the number that's being taken to the x power, B is what we call the constant multiplier or the growth factor. The value of B is what's going to determine whether this is growth or decay. Decay just means a decrease, right? So here it is. If B is greater than 1, that always gives us growth, exponential growth. If B is less than 1, that always gives us decay. So always. Okay, so what do those things look like? Here's an example. If we look on the XY plane, this is what an experimental or exponential growth model always essentially looks like. Now, there's some things we could do to slide this curve around, but for now, we're not going to mess with that. We're just going to, this is what it's always going to look like. Looks like that. Starts very low and very slowly growing, and it just picks up speed. Let me draw that just a little better. Like this. And it picks, that's much better. And it picks up speed and it starts to grow. And when you hear the term in everyday lingo, it's growing, it's getting bigger exponentially or something. Well, that's what we mean. It starts to pick up speed and grow faster and faster and faster. Okay, now there's only one thing about this. Well, there's two things. The shape is important. So a exponential growth curve always has that shape to it. Starts slow, picks up speed. The other thing that's important is, what are the coordinates of that point going to be? Okay, now let's think about this. That's going to be when x is 0, right? Because it's on the y-axis. Agreed? Okay. Let's put all. No way. Headphones and all that stuff. Has to put all those things away, please.
No, I'm not actually listening to anything.
Okay, but I don't even want you to be distracted by it right now. Just put them away and deal with it later. Okay, so what about? That's fine. What about this? What about this? So if we want to figure out what the value of y is going to be when x equals 0, all we have to do is plug 0 into our function, right? So if y equals a times b to the x, what is a times b to the 0? No, it's not. Now think back to our properties of exponents. Any base to the 0 power always equals 1. Aha. So in this case, because that equals 1, y would equal a, right? So the coordinates are 0, a. So the y-intercept of an exponential growth or decay function is always just the initial value. Makes sense, doesn't it? That's why we call it the initial value, or the start value. That's the value we start at when x is 0. Okay, what does a decay function look like? It's very same idea, only it's starting to decrease very rapidly and tails off with time. So it does something like that. Isn't that nice? That's a good curve. And so, same idea here though, right? The coordinates of that point are still going to be 0a, only it's going down this time. Okay? That's it. That's what the graphs look like. Okay, now let's do some examples with these things, and you'll see how useful they are, but really simple to use. Okay, what about this first example here? So, here's the model we just talked about, experimental growth or decay. So we're going to look at U.S. natural gas consumption in trillions of cubic feet per year, or, we're talking about yearly usage, from 1940 to 1970. Now, we're going to let T this time as our variable. Normally we'd call it X, sometimes we might call it T. T is the number of years since 1940. So in 1940, T would have a value of 0. In 1941, it would have a value of 1, etc., right? So I want you to do some stuff with this. Based on this model right here, first of all, find the constant multiplier or the growth factor. Yeah, it's 1.07, that's it. That's the number that's being taken to the variable exponent, right? That's what we call the constant multiplier or the growth factor. So that answer is 1.07. That's simple, okay? Find the initial value or the start value. 2.91. It's that simple. If I wanted to, we won't even take the time to do this, but if I wanted to estimate the yearly consumption for the year 1966, what would I do? Right, make T equal to the number of years since 1966. Well, what would that be? 26, right? 1966 minus my starting year of 1940 would just be 26, right? So we're going to turn that into T equals 26, and our answer would just be Y equals 2.91, run out of space, would just be Y equals 2.91 times 1.07 to the 26. Whatever my calculator tells me, that's the answer. Just throw it in the calculator. Simple. Okay? Questions? Yeah, that's it. That's it. Yeah, it's no big deal. Okay, so what about this? Another example. Same stuff. This time we're looking at album sales from 1982 to 1993. So what's the constant multiplier here? Yeah. 0.39, no big deal. Initial value? 265, and this is in millions of album sales. And then of course, we could easily figure this out too by just plugging a value in, right? Okay, so I want to add one little change, not really a change, just an addition to this idea. There's a way we can oftentimes rewrite our exponential growth or decay model that's very useful. If we want to talk about percent growth or percent decrease or percent decay, percent depreciation, stuff like that, the percent that a quantity is decreasing on a yearly basis or the percent that it's increasing, we want to rewrite it like this. Now what do we do? Very simple. All we did was we took the constant multiplier or the growth factor and we just rewrote it as 1 plus R, where R then ends up being the percent growth, well, right down here, percent growth or percent decay. I forgot to put something that's very important as a decimal. Okay? It's going to be, R would be a positive number for growth. It would be a negative number for decay. Okay, so let's go back and let's just take these last two examples and I want you to tell me what's the percent increase or decrease in this. Percent increase or decrease. Now, how would I do that? Okay, so 1.07 is the growth factor, right? So I just have to write 1.07b. I have to write that as 1 plus R. So what's R? 0.07. Okay, but I want to write it as a percent, right? So if R, in this case, if R equals 0.07, that just becomes, 0.07. That becomes how many percent? 7. I moved the decimal over 2 places. 7%. So, and because it's positive, we would say that our answer is 7% growth or increase. Okay? So in other words, the gas consumption is increasing at a rate of 7% per year. Okay? What about this other example down here? Let's look at this guy again. percent increase or decrease for this guy. Okay, so this time we've got B, you told me the growth factor was 0.39. So we got to set 0.39 equal to 1 plus R, right? What do I do to solve for R? Subtract 1. That's all I have to do is subtract 1. And I end up with R equals 0.39 minus 1. No. Positive 0.39 minus 1. Yeah, negative 0.61. Okay. So if R equals negative 0.61, now pay close attention to this. How do we interpret that? What's that percentage going to be?
Negative 61.
Okay, good. It's 61. It's negative 61%. But the way we would say that then is it's 61% decrease. Okay, the negative sign just tells us that it's decreasing, and the percentage of rate at which it's decreasing is 61%. So we would say that album sales decreased
That sucks.
at a yearly rate of 61%, or 61% decrease in sales per year.
That's terrible. Stop buying.
Yeah. You don't see them, but it's coming back a little bit. Album sales coming back. All right, but I digress. Okay, how about this one? Let's write this as an exponential growth or decay model.
Wow.
So in 1965, the federal debt of the U.S. was $322.3 billion. During the next 30 years, the debt increased by about 10.2% each year. So I want to write that as an exponential growth or decay model. So what's that going to look like then? Y equals, now what's my value of A going to be? What's the initial value? Good, 322.3 times what to the x? Okay, now, what about that? That's 10.2% increase. So if I want to write that as a decimal, when they give it to me as a percent, I want to immediately write it as a decimal. So R is 10.2% increase. Which becomes what as a decimal? 0.102. I got to move the decimal 2 points to the left to make it right, to make it smaller, to make it a decimal. So 0.102, and it's positive because it's growth, right? Okay. So then down here, what am I going to put? That number plus 1, right? It's 1 plus R to the x. And so I could actually combine that into one number. And I just get y equals 322.3. What is 1 plus? Yeah, 1.102. Okay, make sense?
Yeah.
There we go. That represents 10.2% growth of an initial amount of 322.3. That's our answer. Yeah, that's it. That's it. Okay, what about this? Same kind of thing. We buy a new car for $22,000. The value of the car depreciates at a rate of 12.5% per year. So it's decreasing. Good. So if we want to find R, so it's decreasing. So R is what then? Okay, negative because it's decreasing. Yeah, negative 0.125. Let's remove the decimal. Okay. So then, if we want to write this model out, what's our initial amount?
22,000
Times 1 plus negative, so 1 minus 0.125 to the x. So that's just 22,000. What's 1 minus 0.0125? 0.875.
I told him that.
That's it.
Why do you need the one?
Okay, why do you need, good question, why do you need the 1? Because in order, we have to know, we need the 1 because if we want to turn this into a single amount, we got to know that the percent increase or decrease as a decimal is always what is being added to 1. See what I'm saying? So we got to get from here down to a number to the x. And the way we get there is we always have to, that is the ultimate value of the constant multiplier or the growth factor is 1 plus the percent increase as a decimal. Make sense? So we do need the 1 there, okay? Okay, so you got that. I mean, that's what that stuff is about. Okay, so a couple more things. It's also, you get a ton of useful stuff in one day. It's all pretty simple. This is a good day for you. The natural number. Now, as you go on, non-seniors, you guys will get a little shot of this before the end of the year. Seniors, this is probably it for you. But I want you to at least be introduced to this because you'll see this again next year in math. The natural number e. Oftentimes, when we're taking we're dealing with exponential functions or their inverses, logarithmic functions. The base that shows up in the real world is this constant number called the natural number e, or Euler's number. It keeps going. It's just like pi. It goes on forever. But we don't write it as a decimal typically. If we do, taken out to 5 places, that's what it is. But just like pi, we don't really write out a number. We just use the symbol pi to represent that constant, that natural constant. Here, the symbol that we use is a lowercase e. In math, when you see a lowercase e, you know that means this natural number. Yes, sir?
So how do they just take a random number decimal? How do they come up with
No, the way they come up with that is when you actually model like the growth of bacteria, or you use a mathematical way to come up with it. But the reason this is important is because when you actually look at the way a population works, that's the number that pops out every time. You look at radioactive decay, or you look at, that's the number that always comes out. That's the way it works. When you model it, that needs to be the base. Okay? So that's why it's called the natural number, because in the natural world, it shows up all the time. When you study calculus, you'll get an idea, a much more solid idea of how it really works. Why do we get that value? But for now, we have to just kind of trust me on that. Yeah.
Is this the same number that you would use to find the rate of decay?
Yes, it is.
That's what you
Yep. Yep. In fact, that's what eventually, non-seniors, we're gonna do a little bit more with that.
That's what we're now.
So, right?
We're not students, but we're-
Okay, so what do we do with this? So, almost nothing. This is a section that you essentially get for free because manipulating or simplifying expressions, listen please, manipulating or simplifying expressions involving e just uses the very same properties of exponents that you already know. For example, if I wanted to simplify this expression right there, what do? I mean, that's easy because it's just e is just a constant, right? So I'm going to use my properties of exponents. If I take a product of two things, 3 and e to the negative 3x to the negative 1, what does my property of exponents tell me I do? What do I do with that negative 1 power? Distribute it, sure. I'm just going to distribute that through. So it goes to both parts, right? So what I end up getting is 3 to the negative 1 times e to the negative 3x times negative 1. What's that? 3x, yeah. Negative times a negative is positive. And so if I simplify that, what is 3 to the negative 1? No, what's it mean if I have a negative exponent? No. A negative exponent, all that means is it's positive on the bottom, right?
So it's gonna be 1 there.
Yeah, so it's going to be 1 over 3 to the 1. I don't even write the 1, right? And then on the top I don't want the 1 there, do I? On the top, I get e to the 3x. That's my answer. Yes, ma'am.
Okay, so the negative 1 exponent, it won't affect the e just as exponent?
Right,
Okay.
right, because it's e to this power, and if I take a power to a power,
Yeah.
I just multiply the exponents, right? Okay? Another one. What about this guy?
Is
Is that 6?
Oh, hang on. That's not what I want to do. Never mind. Not quite there yet. Okay, I got another example I want to quickly look at. Where's all my notes? Okay, how about this guy? Yeah, very good. Okay, don't get sidetracked. No discussions. Stop.
Sorry.
There we go. Okay, what about this one?
2x, or sorry, my bad.
Okay, well, I gotta simplify this whole thing. Let's just look at the numbers at the fraction part. Does that simplify?
2e.
No.
The 6/4, is that reduced?
Yeah.
3/2, sure. Okay, now what about the e's? That was the easy part. What about the e's? If I've got like bases, if I divide like bases, and that's all we have here is the base e to the 3x divided by the base e to the what?
No.
To the 1. Okay. So if I divide like bases, what do I do to the exponents? Subtract. So I just get e to the
2x.
3x. Hang on. 3x minus 1 is not 2x. It's 3x minus 1. They're not like terms. Right? It's just that.
Makes sense.
Okay?
And that's your final answer?
That's the final answer.
That's a compass test answer?
Yes, it is. Yes, it is. Okay.
My bad.
Okay. No. Tuesday. I think it's Wednesday. Yeah. Tuesday or Wednesday. I think pretty sure Wednesday. No, it varies. Don't ask me now. It's nothing to worry about the number of questions. You'll be fine with that. That's right. I'm in the zone. Okay, here's one. Oops, no. Growth or decay? We're playing the game growth or decay.
Uh-oh.
You tell me.
Gross.
Okay, so let's look at this now. If I want to write this as an exponential function, face front, there we go, thank you. If I want to write this as an exponential function, I just have to think of this in terms of this form. A times b to the x, right? Now, what part of that determined if it was growth or decay? Okay, b. If b is positive, it's growth. If it's negative, or if it's less than 1, sorry. If it's greater than 1, it's growth. If it's less than 1, it's decay, right? So we got to rewrite this in that form. Well, what's a? 5. Okay, but if I want to write this as something to the x, how am I going to take this stuff right here and write that as something to the x? This is a little bit tricky the first time you see it, but can somebody tell me? Now we've got a property of exponents that says if I take a power to a power, I multiply the exponents, but I can also reverse that. So it's going to be 1 over e to the 3 is exactly right. Here's why. Watch, please. E to the negative 3x, we could write, if I take that x and just factor it out at the top, I can write that as e to the negative 3 to the x, can't I? Because a power to a power means I just multiply the x by the negative 3. I can go backwards with that property, right? So then e to the negative 3 is what goes there, right? Now what is e to the negative 3? A negative exponent on top is positive on the bottom, so that just becomes a 1 over e cubed. Now e is a number that's 2.7-ish, so 2.7-ish cubed is going to be 25-ish, right? It's going to be a pretty big number. That's roughly like 1 over 25-ish. Is that going to be a fraction that's less than or greater than 1? Yeah, quite a bit less than. 1/25 is a small number, isn't it? So because this number right here, because that number is less than 1, we know this is decay. Decay is the winner this time. Okay? Okay, what about this guy? Very similar to what we just did. If I want to write that as a times b to the x, what's a? 1. Yeah, okay, good. So I get 1 times...
1 over 6.
Okay, good. E to the negative 6 to the x, and so that just looks like 1 over e to the 6 to the x. Obviously, is that growth or decay then? That's going to be decay. That's a really small number. 1 over e to the 6 is pretty big, right? Okay, good. All right, so you got it. Okay, last issue. Last issue. This one you got to pay attention to. It's not hard, but you got to really pay attention to this. Okay, so logarithmic functions. Now, if you're a senior, this is probably your only shot at this. We'll spend a little more time on this, but I'll tell you, even if you're a non-senior, Chapter 8 is it for us. Chapter 8, we're not even going to do the whole chapter, but there's a few parts I want to do that are pretty cool and interesting, and this will be a good way to end the year. One of the things we're going to briefly talk about is that logarithmic functions are the inverses of exponential functions, okay? So for now, the only way that causes an important relationship to exist, and that's all we need to know about is this relationship. Whenever you want to write a logarithmic function like this, and here's the way we would read this. We would read this as the log of y base b, or the base b log of y equals x. That's not going to mean a lot to you. And honestly, it never really will, because we don't think in terms of logarithms very well. It's not the way our brain works. We have a much easier time thinking in terms of exponents and powers. So what you always want to do immediately, whenever you encounter a logarithmic equation or expression, you always want to rewrite it in terms of exponentials. So write it in the exponential form. Now, if this is the logarithmic form, this is the exponential form. And here's what you do. It's very simple. If you remember the phrase, a log is an exponent, that really helps. So whatever the log is equal to on the other side, in this case x, is just going to become the exponent of the exponential form, right? A log is an exponent. Whatever the log is equal to becomes the exponent. Now the base of the log, this is really simple. The base of the log just becomes the base of the exponential. And then what's left? Well, whatever was inside the log, the y, is going to stand by itself. Okay? So let's look at an example of how that's very useful. What if I want to try to solve for x here? Okay? Exactly. That doesn't mean much right there. Log 32 base 2 equals x. I mean, who knows? But if we write this as an exponential, it's pretty easy. So if we write that as an exponential, what goes where? We always want to fill in the blanks. We're going to have something to the something equals something. Okay, good. So 2 is the base, right? The base of the log and the base of the exponential. What goes here? Yeah, whatever the log is equal to becomes the exponent. And that's just 32, right? And so if we do that, now that's pretty simple. We can solve that. 32 equals 2 to the 2 to what power? We'll find out. 2 to the 2 is 4, to the 3 is 8, to the 4th is 16, to the 5th is 32, right? So because, that makes sense? So because 32 equals 2 to the 5th, we know that x is 5, right? Okay, very useful. Okay, let's try another one. How about this guy? Okay. Oh. Yeah, here.
Little curves are getting fancy, oh yeah?
Yeah. How about that one? If I want to solve for x there, gotta do the same, play the same game. I just want to rewrite this as something to the something equals something. Hey, don't get distracted. Jacob, put that phone away. Quick. Yes. Okay, good. So 2
Oh, bad shot.
to the 5th equals x. Now that's easy, right? We can do that.
We just had it.
We just had it. So it's 32. It's hard to think of this way, but if you write it as an exponential, it's easy, right? Okay, so I want to know here.
Is that really it? I know.
Yeah.
Oh, yeah, we're tricking us.
Well, I'm just gonna go through a couple more examples, but yeah, that's really all
You're
for the
tricking us.
for the compass test. That's really all we're gonna do. Well, I'll add a few more things after that, but this is like 4 sections in the book. Seriously.
You just go to 4 sections?
Yeah, chapter 8 is it's exponentially easier than the other stuff. Do you like this? See what I did there?
No, pretty good.
Okay, how about that? Okay, listen please. So if I wanted to solve that, I can do that. All I have to, same stuff I just did. If I'm trying to solve this logarithm, all I gotta do, the answer I'm trying to find, we'll just call x, right? If I set that equal to x, now I just have to rewrite that as an exponential form and solve for it. So what's that gonna look like?
7x equals 343.
So we just count. 7 to the 1 is 7, to the 2 is 49, to the 3 is 343. So it's 3.
Tell me I'm wrong then, right?
Piece of cake,
Socks.
right?
Oh, so X.
I mean, for now. Okay, so here's the other thing. Later on, there's a possibility I might add just one tiny more thing. Because what happens if the number was like, I'm not going to do it today. What if the number was log of 200 base 7? Hey, I'm losing some people. Stop. The log of 200 base 7 equals x. Well, 7 to no power is 200. So how would you fix that? There is a way you can solve that using some properties of logarithms that are useful. Okay, but I'm not going to get to that today. We'll get to that. I'm going to put that off. I tell you what, I will do that. I will show that. I'm going to show that to you because it's so simple and so useful. I'll show it to you Monday, and then we'll go to the left. It'll take 5 minutes. Okay, so how about this? Okay, what's that going to be? Now let's see if we can do this one even without rewriting it. Okay, think about this. Whatever this is equal to, call it x, right? Whatever that's equal to, if we well, let's rewrite it. Let's go ahead and rewrite it. So we rewrite that as b to the x equals 1. Now, I didn't even specify what the base was. The base could be anything. Anything to what power always equals 1? 0. So the answer is 0. That's always true. The log of 1, any base, is always 0. How about this one? The log of b base b equals what? Now, if I call that x, that's like saying b to the x, right, equals b to the 1. So what's x? 1.
And these are always true.
Yeah, those are always true. Okay, now let's get specific. Well, I want you to simplify this. How about, that's the game we're playing now. Simplify this.
Playing a game now?
Yes, we are. Okay, well, here, I'll show this. I better show that to you. Okay, so just in mathematics, there are 2 bases that we use a lot. I told you we use the base e a lot because that's what matches naturally occurring phenomena. And when we write a base e log, we don't want to have to write that whole thing out every time. And so we give it its own special notation. We call it the natural log.
Would you please meet with Mrs.
And we write it as
Calendar
ln
at this time? Orchestra
x.
students, please meet with Mrs. Calendar at this time.
But what that means, ln always just means, is that you?
Yeah, I play the viola.
Okay, so ln, listen please,
I
listen.
played it with students in there.
Yeah, go.
No, that's not.
I'm just-
Yeah, I know you are.
Orchestra.
Okay,
What's a viola?
Viola.
a viola is what we talk about if we didn't have 10 minutes left in class, but for right now, we're not going to talk about it. Okay, so we write log base e as natural log, ln. That always means the base is e though. If it's a base 10 log, well, that's another really common one because we have a base 10 number system that we use.
Michael, Ray, come to the office, please. Michael, Ray,
And
come
so,
to the
I'm
office.
getting tired of those interruptions. And so we'd write that this way. We just what's called a common log, and we wouldn't even bother writing the base. If the base is 10, it's sort of like putting a 1 in front of an x or something. Hey, listen, please. It's like putting a 1 in front of an x. We just don't do it. We know it's there, but we don't do it because we don't need to. We get lazy. Or when we write a square root, it's really a second root, but we don't write the 2. Same thing here. A base 10 log, we just don't even write anything, and that means that we assume in that case that it's a base 10 log. Both of these you can do right on the front of your calculator. I'm not even going to show you because it's so simple. One of the buttons is LN, the other one is LOG. So you probably figure that out. Okay, I already did that one. So let's do a different one. Now we're playing the game Simplify This. And here's how we play the game Simplify This. The game Simplify This. Let's see what we want to do.
Yo, loser.
So, how do we do? What do we always do when we're trying to? What do we put on the other side? X. Yeah. Or call it. Maybe we already have an X there. Let's call it Y.
Okay.
Okay. So then, if I rewrite this, what's it look like?
2 to the y equals
2 to the y equals 2 to the x. So what is y equal to? If 2 to the y equals 2 to the x, y must equal x. Yeah. And so that answer is x. Okay, right? Okay, how about this guy? Okay, so what do I call that? Andrew, put that away. What do I call that? Y maybe? Does it already have an x? Right, so if I set that equal to y, what is it? 20 to the y equals 8,000 to the x. Okay, so the only way this is going to work for us for now is if I can somehow make the bases look the same, right? So can I do that? Now, can 8,000 be written in terms of a base 20? In other words, is 8,000 20 to some power?
Yeah, I'm gonna
It
get
is.
to, I'm gonna,
20 to the, no,
yeah,
3.
I was close, I was close.
Right, because think about that. 20 times 20 is 400, times 20 is going to be 8,000, right? So I can write that as 20 cubed to the x. Okay, so then what is, if I simplify this side, take a power to a power, what do I do? Okay, well, okay, in this case, meaning multiply, right? So I'm going to get 20 to the y equals 20 to the 3x, so y must equal 3x. So my answer, my answer is 3x. Okay. All right, last 2 problems for today. You're getting this though, this is good. It's not too bad. Okay, I want you to find the, now, this sounds really tough, but this is so simple. Find the inverse of y equals the log base 1/4 of x. Okay, now, super simple. What do we do? What's our recipe for finding an inverse? Yeah, switch x and y, solve for y. Easy, right? So all I got to do here is I'm just going to swap those. So I get x equals the log of y base 1/4, and I got to solve for y. So all I have to do is rewrite that thing, right? If I rewrite that as an exponential function, what does it become? Okay, 1/4 to the x equals y. There it is. Yeah, easy, right? Piece of cake. Piece of cake. Okay. How about
One more.
one more? Yeah, let's do, oh, here's a good one. Oh, I like this one. Okay. Yeah, how about that guy?
Oh, is that an LN?
Yes. So what does LN mean?
Length.
Population, natural population.
Okay, yeah, but what's the base that goes with E? Okay, so when we see a natural log, we always know that that's a log with a base E, right? Okay, so if we're gonna find the inverse, we're just gonna swap the x and y, right? So this just becomes x equals the base E log of 6y, right? So if I rewrite that as an exponential function, I got it. What do I do? E to the x equals 6y. Very good. So then what's y equal to? 4. What do I do to get the y by itself? Yeah. Just divide by 6, right? Or multiply by 1/6. Right? All I'm doing is dividing both sides by 6 now, right?
Wow.
Piece o' cake. Am I right?
Yes.
Okay, very good. I will put those assignments up. I'll make them short and sweet. Okay, here's the deal. Here's the deal with this, guys. What I'm going to do, I'm making a decision, game time decision here. I'm either going to make this a big assignment in terms of value, very few problems, or I might even make it like an at-home little test, sort of like a half test that you can do at home. Very simple. Either way, you'll have access to it.